Hi, this video will cover section 3.3, Properties of Logarithms. And the objectives for the section will be to use the change of base formula to rewrite and evaluate logarithmic expressions, to use properties of logarithms to evaluate or rewrite logarithmic expressions, to use properties of logarithms to expand or condense logarithmic expressions, and to use logarithmic functions to model and solve real-life problems. So section 3.1 was all about exponential functions. Section 3.2 is about properties of logarithms. And what we're going to do after this section is we're going to start applying the concepts from the previous two sections with and use the properties to manipulate logarithmic expressions and to solve exponential equations as well. So one of those that we're going to go over is the change of base formula. And I have been talking about how your calculator does have two buttons to calculate a logarithm. Some of the new ones now you can enter any base, but a regular calculator will have ln and log for log base e, and this one is base 10, log, just log without the base. So if you wanted to find a logarithm of a different base that was not 10 or e, then you will have to use the change of base formula. And what that implies is that you could use either a base 10 logarithm, as you could see here. So we just have log, or you could use base e, or ln. That's why we have ln. And so what you're going to do, that's how you change the base. You change it to a base 10 or a base e. And what you do is you create a ratio of two logarithmic expressions. So I want you to notice how this expression is not the same as just saying log of x over a. That is completely different. So we don't want the log of a ratio, we want a ratio of two logs. So you have log written twice, one for the numerator, one for the denominator. If you choose to use base e, you will still have ln written twice, ln of x divided by ln of a. And when you enter something like this on the calculator, you have to make sure that you type that either log or ln twice, one for the numerator, one for the denominator, but we'll do some examples. And this is the way you will apply it. So if you start with an expression such as log of x base a, so here we have the base a, and the argument for this expression, it is x. And so what we do is we choose a base, whether it's 10 or e. Here we have just a general example of base b, just to call it a number. And you could see it here and here. So you create a ratio where you take the log base b of x and divide it by the log of a base b. So what you're going to do is take the argument, which is the big quantity, and you are going to use the argument as of the original logarithmic expression as the argument of the ratio of two logs. So log of x, and remember this is base 10, that's what we're talking about, and we're going to divide it by the log of the little number, which is for the base, so divided by the log of x. So to give you an example, if I have log of 5 base 2, the change of base will be log of 5 divided by log of 2. And here I don't need to write a base because I know that it is an implied 10, but I'm just going to write it for you there. So that's it. That's how you do the change of base formula. They're easy questions on your homework about it, and of course you will need your calculator. Now, if we were to use ln instead, it will be the same idea. You take the ln of x, as you can see here, and divide it by the ln of a. So we could also get the same as the previous example, ln of x divided by the ln of a. So we have the argument on top and the base on the bottom. And of course, we do have the abbreviation for natural log, ln, twice, because we're taking the ratio of 2 logs. For example 1, we have the expression log of 25 base 4. So this will be something like, to what power do you have to raise number 4 so that you can get 25? So it is obviously not an easy one to find. So what we do is we use the change of base. And you can see here, this has already been written with base 10. So I enter that on the calculator, and what I get is approximately, and I'm going to round to the nearest, what would that be? 10,000. So that's that will be 4 digits after the decimal point. So that will be 2.31. Hold on. 2.3. 219. Now I could also get the same answer if I rewrite it with the base e. And so for base e, we will be using the natural log, so it's ln of 25 divided by ln of 4. And this will give me the exact same approximation as the previous one. Now, when you enter this on the calculator, make sure you do enter natural log, and then you might need parentheses. Sometimes when you enter natural log, the calculator will open the parentheses for you. Then you might need to close it. Then you enter your division key. Then you enter ln again, you must, and then the other number, which is 4. And so the same rules will apply if you decide to use log base 10. Okay, so now starting with the properties of logarithms. So we are gonna go over these properties, and we're gonna learn how to go from something that we call here the log of a product. You could see here we have two things multiplying, u and v. They are the arguments of the logarithmic expression that are multiplying, and that's why we call it product property. So we're going to go over that. We will also go over the quotient property, so that implies division. You can see here for the argument you have 2 letters in this case. They could be algebraic expressions, they could be binomials, monomials, they could be a number, they could be a variable or a combination. So, but the idea is that they are dividing each other, u and v. And then we will also go over the power property, which is just like the name says, it is going to involve an exponent, which is the n right there. So before we get started, I want to just give you a little reminder of how the properties for exponential quantities work. So, for example, if you have a to the power 2 and you multiply that by a to the power 3, you need to add the exponents. And so if you are multiplying the variables, you add the exponents, so it will be a to the power 2 plus 3, which is 5. Now, that concept of multiplying and then adding the exponents, it kind of translates into logarithmic properties. Remember how we discussed that exponentials and logarithms are inverses of each other. So here we have two things that are multiplying, u and v, and we're going to expand it into something that will be the sum of two logs. And so I'm going to write the name here. So on the left side, what we see here, it's called the log of a product, and it turns into the sum, or the addition of two logs. And that's a way you can remember it. We're going to do some examples. Same rule applies to natural log, base e, or base 10, common log. So we have ln of u times v, so we can expand it into the sum of two logs. So when we go from left to right, we will refer to that as expanding. We expand from something that has one log into something that has two logs. Okay, now let's go over the quotient property. So I want to remind you how if we had a to the power 7, let's say, divided by a to the power 5, in this case we are dividing two variables that are the same but different exponent. So we subtract the exponents. That is the rule. And here we will get a to the power 2. So we go from something that is dividing, that's the quotient, to something that is subtracting the exponents. So you can remember it that way. We have the quotient property, the log of a quotient, that's how we call it. This side here, log of a quotient, and we expand it as the difference of two logs. Difference because we have a minus there. And in this case, it does matter which one has the positive and which one has the negative sign. Difference of logs. So whichever argument is in the denominator, that's the one that will have the negative sign in front of the log. And whatever is on the numerator will have that, it will be at the front, or will have a positive sign in front of it. If it's at the front and it doesn't have a sign, then you assume it's a positive sign. And again, if we go from left to right, we refer to that as expanding. Now, if we wanted to go in the opposite direction, we could go from the sum of two logs and then condense that into the log of a product. So going in this direction, we refer to that as condense. to go from something that has more than one log into something that has only one logarithmic expression. These two properties are very useful when we start solving equations and, of course, word problems. Same property applies to natural log, so the ln of a quotient will be the difference of two natural logs, natural log of u minus natural log of v. And the third property that we have here, oh, and just to clarify, you could also go in the other direction here. The difference of logs could turn into the log of a quotient. And here finally we have the power property. So for this one, what I want you to think is how we're gonna have the exponent here. Here the base is n. Oh no, the base is u. And n is the exponent or the power of the argument. The argument is u and the base is a. I'm sorry, this is the base. So what we do is we take that exponent and we bring it to the front of the expression here. And the way it will turn is n times log of u base a. So the idea is that we have the log of u multiplied by itself. We don't know how many, what n equals exactly, but we know we have u n times. And so if we were to apply the product property, the one that moves, not moves, but expands into a sum of two logs, then we will have something like the log of u base a plus the log of u base a, and I'm gonna need more space. And we have that addition repeating. We don't know how many times, but we know is n times. So if this was 3 times, we could just say 3 times log of u base e. So what we say instead is n times the log of u base a. So that property is extremely useful. We are going to use it like maybe 80% of the time or 85% of the time when we solve either word problems or just simple equations. So you could also see it here. So the n becomes the coefficient. So it goes from being an exponent to a coefficient. And so, of course, it also applies to the natural log. So you could see here is the natural log of u to the power n. So we could take that and put it in the front as the coefficient. There's no sign between n and natural log, so we know there is an implied multiplication. And so those are the 3 rules: product property, quotient property, power property. So on the next example, we are going to learn how to apply them. We need to write each logarithm in terms of ln of 2 and ln of 3. So we have on our first part ln of 6. And so we know that if we were to multiply for the argument 3 times 2, that will give us 6. So now we have the log of a product, and what we're going to do is expand it into the sum of 2 logs, because that's the product rule or the product property. So then this will be ln of 3 plus ln of 2. Addition is commutative, so this will be the exact same thing as if we had that. Okay, for the next one, we are going to use the quotient property. So we have the natural log of 2 over 27. And so this will turn into the natural log of 2. And you notice that sometimes we see parentheses, sometimes we don't. If you only have one term as your argument, it's fine if you don't have parentheses. But if the argument was to be 2 plus x together, then we must have parentheses, because we don't want the calculator or the computer or people to think that we're only taking the ln of 2 and then adding x at the end. So if you want x to be part of the argument, you must put it in parentheses. Here we don't have x, so I'm just gonna delete that. So if you're not sure and it's just one term and you put the parentheses, it doesn't make it wrong. So it's just to be safe. So here from the quotient property, we go to the difference of 2 logs, or in this case, natural log. So ln of 27. Now here, we're not really doing what they ask us to do, because we need to write everything in terms of natural log of 2 or natural log of 3. So what I need to do is change the ln of 27 so that it reflects this one here. So if you think about it, 3 to the power 2 is 9. And if you multiply by 3 again, you will get 27. So 3 to the power 3 is 27. So I'm going to change that. And now what I want to do is use the power property, and I'm going to bring that to the front. So the little 3 goes from being the exponent to being the coefficient of natural log of 3. And we don't need to evaluate. If you notice the instructions, we only have write each logarithm in terms of that. It doesn't say evaluate. If it said that, then yeah, we will have to put it in the calculator and look for an approximation. Okay, for example, 5. So for example 4, I want you to write that as well. We're going to do 2 examples of evaluating a logarithmic expression without using the calculator. So for example 4, we're going to evaluate the logarithmic expression without the calculator. We're going to use some of the properties that we learned on the previous section, 3.2. And what we're going to do here is I'm going to try to change the cube root of 5 with something that is of base 5, just like the base of the logarithm. So this will be the log base 5 of 5, and you notice the index of the root is a third root or cube root is a 3, so that would be 5 to the power 1/3. And that is what happens when you have exponents of fractions that are representing the index of the root. So here, the argument matches the base, so we can cancel that out, and the only answer is not 1/5, but 1/3. 1/3. And that's it, that easy. You do not need a calculator for that. We have here natural log of e. Remember that natural log is already base e. So here the argument and the base match, so cancels, and the answer is 6. For the next one, same thing, the base matches the argument, so the answer is 2, so 6 minus 2 equals 4. And let's see. Okay, that's it for now. Let's move on to the next example. So for example 5, we are going to expand each logarithmic expression. So that's when you go from something small to something bigger. So we're going to go from, you can see here how the 5, the x cubed, and the y, they are the log of a product. And we're going to turn it into the sum of logs. So for that, we are going to separate the log base 4 of 5 plus log base 4 of x cubed, and then plus log of base 4 of y. When you're entering your answers on WebAssign, writing the correct base is very important. So even just leaving the base blank, it will count it as wrong. So don't do that. Then here we could do something else. Log base 4 of 5 plus, and I can use the power property, bring the 3 in front of log, and it will be 3 times log of x base 4. And then finally here we will have log of y base 4. And that's it. Now the next one, I want to actually make it a little bit more challenging. I think it's just too easy the way it is. So I'm going to go ahead and add another variable here. I'm going to put y. Okay, so you could see that you have the log of a quotient. So this one is going to go from the log of a quotient to a difference of logs. So here we have 3x minus 5, and then minus we have, oh, and I'm saying log, we have to keep the same base. So it must be ln of 7y. Okay, so I am going to rewrite the square root as an exponent. So because the index is a 2, it's an implied 2, we don't see it there, but we know it's a square root, so then it will be the natural log of 3x minus 5 to the power 1/2 as a fraction. And then what I notice here is that natural log of 7y has a product in there, 7 times y. So I can go ahead and simplify that into the sum of 2 logs. So ln of 7 plus ln of y. But after that, I'm going to have to, and before I do that, let's go ahead and use the power property here. So we will have 1/2 times natural log of 3x minus 5. And now what I need to do is distribute this negative sign to everything inside the bracket. So it will be negative ln of 7, and then again negative times ln of y, so negative ln of y. Now, one way to do this at once without having to do this step here, like keeping 7y together is that you could see from the beginning that they are both multiplying, but they're both in the denominator. So because they are at the bottom of the fraction, on the bottom of the fraction, they will both have a negative sign in front of them. That's the shortcut of it. So I could have just said this part here is gonna have the square root, or I could just use the expression with an exponent, 3x minus 5 to the power 1/2. And then it's going to have minus ln of 7 because the 7 is on the denominator, and then denominator, and then minus ln of y because the y is also part of the denominator. And then, of course, you remember to move this one to the front. But I mean, in reality, the steps that you take, the order of the steps, in this case, they do not matter. As long as you get the correct answer. Now, if you were to go the long route but you forget to distribute the negative, then you will be doing something wrong. So I do like to look at what's in the denominator. Remember, I included that y, and just take those and make sure they do have a negative sign in front of them, like that. Now, if you are wondering why I'm not separating this quantity, is because that's not a product. That is the log of just a difference. It will have to be the log of a quotient for us to be able to separate it, or the log of a product. Okay, now we do not have example 6 on this PowerPoint, so I'm gonna grab one from the textbook. Okay, so here is example 6 from the textbook. And now we're going to go in the other direction and condense each logarithm. So we're going to go from 2 logarithms. Here's one of them. Here's the other one. To only one. That's what the word condense means. So at the end, you only need to have the word log once, and that's it. And then whatever else you need. So the first example, we do not have a base. We know it's a base 10. We don't need to write it, but we need to verify that it's the same. So what I'm going to do first is apply the power property in reverse, like that. So, and also with the 3 here. And so we will get log of x to the power 1/2 plus log of x plus 1 to the power 3. That's what we will have. So the power property was used in reverse. Then from there, we notice that we have the sum of two logs adding. And so we're going to go to the log of a product. So this is going to turn into log only once. Remember what I told you, we only want to write it once. So it's going to be log. We don't need to write a base because it is base 10, and it's going to be of x to the power 1/2, and then times, I'm going to actually erase this here, times x plus 1 to the power 3. So it could look like something like that. And of course, we could simplify it a little bit, or just change the exponent so it's an actual square root. So it could be the square root of x times x plus 1 to the power 3. And that could also be a good way to write the answer. Now, the next one, we will do the same thing. First, apply the power property in reverse, make that coefficient turn into an exponent. So we will have ln of x plus 2 to the power 2. Then the minus here, well, let's just write it here and we'll change it on the next step. So now the minus sign implies that you're going to have the log of a quotient. So the fraction that you're going to have is going to be the argument that is preceded by a positive sign or no sign, which denotes positive. It will be on the numerator. So x plus 2 square. And then the term that has the negative sign in front of the log, it will be the denominator. So in fact here, I don't really need the parentheses in purple. I could just write my answer this way. Natural log of x plus 2 square over x. And of course, you could add the parentheses or use brackets or even not have them because the fraction bar is already a grouping symbol. Okay, the next one. Now we have a 1/3 here. And in fact, I want to make this a little more interesting, so I'm going to make that 1/3 negative. Do I want to do that? Yes, let's do it. Okay, so if we distribute that negative 1/3 to both expressions, we'll have negative 1/3 log base 2 of x. And then we distribute it to the other log, and we will have minus 1/3 of log base 2 of x plus 1. Okay, so one thing we could do is write the negative 1/3 as the exponent of the x, like that. And then here we could have minus, and then the log of 2 x plus 1, and then we can have the 1/3 here. Now, since I already kept a minus here, then this one will be positive, or I could make this positive, but then this needs to carry the minus. Let's do that. Okay, so what that means when you have a negative exponent is that you could switch that quantity so that it is in the denominator like this, 1/3. And then you could also have this other one do the same. 1 over, and then the whole x plus 1 to the 1/3. So if we were to condense this 2 into one logarithmic expression, it will be the log of base 2, of course. And the argument will be 1 over. And actually, I'm going to write this one as a square root, cube root of x. And then here, this one, it could also be a cube root of x plus 1. And in fact, I could also put them together all inside one of the roots. So not base 3, but base 2. If we change the base, then we will be doing something wrong. So this could be 1 over, and then the cube root of x times x plus 1. And then, of course, we could go ahead and even multiply what the x and the x plus 1 will become inside the square root. So, I mean the cube root. So this will be x squared plus 1. Oh, no. Plus x, because we have to distribute the x. This one right here. Okay, so that will be plus x. Okay, now a problem like that could have been just solved if we had done the following from here. We could have just said, we're going to leave that negative 3 there, and then we're going to condense what's in here. So that would be the log base 2 of x times x plus 1. Just like that. And I'm going to just make some room here. So then from there, we could have said that's going to be negative 1/3 log base 2 of x squared plus x. Here I would definitely use parentheses. And then from there we could say this would be log of base 2 of x squared plus x to the power 1/3, negative 1/3 I should say. And of course from there we could say, since the exponent is negative, we could say log base 2 of 1 over x squared plus x to the power positive 1/3. And that is the same thing that we got on the other one. Of course, we could also put them inside the cube root. So we're going to move to the next problem now. Well, just to remind you quickly that whenever you are simplifying, condensing, or expanding, you don't need to only have 2 logarithmic expressions. You could have more than 2. You could have 3. You could have 4, or you could have many more. For example 7, we're going to be finding a mathematical model. And I'm going to read from the slide. So it says the table shows the mean distance from the sun, x, and the period, y. So the mean distance from the sun, and here we're going to look at the different planets that you have listed here. Oops. Here are the planets. So we have Mercury, Venus, Earth, Mars, Jupiter, Saturn. And the x value, the independent value, is representing the mean distance from that planet to the sun, or from the sun to that planet. And of course the units, they are here in astronomical units, where Earth means distance is defined as 1. Okay, so that will be the input, the independent variable. The set of all those distances is the domain. Now the output is going to be the period given in years. And that is the time it takes a planet to orbit the sun, but in years that are like our years, Earth years. 365 days. And that is exactly why you see the same here, 1 and 1. So the mean distance, we're using Earth's distance as a 1. We're using a 1. And then we're also using a 1 to represent the time it takes for that planet to orbit the sun, to complete one full rotation. So you could see how some planets, their distance, of course, they're closer to the sun, like the first 2. And so I am assuming their orbits are smaller. But if you look at Mars, for example, it is further from Earth. It's further than Earth from the sun. However, oh no, it also works. Never mind. Okay, so they all work. They are all further from the sun, and they all have a period that it is bigger. Well, and of course, if you look at the period for Saturn is 29.4, so like 29 years, Earth years. That is the time it takes for Saturn to complete one full rotation. Now, how did they go from these numbers that are representing X to the numbers representing Y? And so the solution to this one is the natural log was used. And so if you look here, the figure 3.18 is showing the plots of the points given by the above table. Okay, actually might be this one here. Yeah. So if you look at here to the x values that we had, to get the values that you have here, the natural log was taken. So for each number there, natural log of that x value of the mean distance. And then this new table was created. So then from there, we got, or the textbook, I should say, that all the y values, the period, and the ln, the natural log of those y values was taken, and that's how these new numbers came to be here. For Earth, we have 0 and 0 because we had 1 and 1 for the x and y values. So remember, natural log of 1 is 0, natural log of 1 is 0. So that's how the new points, for example, the point here 0.421 comma 0.632, which is representing Mars, you could see it graphed right here. Okay, now since this one is a linear function, you could see that we could use one point, and in fact we could use the 2 points that I have highlighted because the one from Earth 0, 0 is the easiest to use. So we could use that point to find the slope of the line, and so that will be y2 minus y1 over x2 minus x1. Now in this case we're using ln of y and ln of x, but just look at the points and try to concentrate on that. So we're going to be using the point 0.421 comma 0.632, and then we're using the point 0, 0 because that is Earth right here. And so that's pretty easy to compute. So it will be 0.632 minus 0 over 0.421 minus 0. And the answer for that will be, it will be 1.5, or we could use 3/2 if WebAssign is being picky and wants fractions or the exact answer. And we see that the y-intercept is at the origin, so that means that the equation is going to be, I'm going to call this capital X. We do this in statistics a lot. We use lowercase and uppercase. Because here, lowercase x goes with ln, and lowercase y goes with y. So here we have this function where we have that x is equal, or actually I should say y. So y is equal to the slope that we have here, 3/2 of x. And if we substitute x and y with the expressions that we have up here, it will turn to be ln of y is equal to 3/2 of ln of x. And that's it. That will be the end of the problem. So the question was just to determine the, I'm going to go back to read the question. Find an equation that relates x to y. So here we go. If we have to solve for y, that is actually the topic of next section, how we could cancel out ln, but I think some of you might already know. I want you to think about having something with the same base. So this is the end of the video.